Have you ever encountered the most bizarre power supply failure involving board explosions? The entire system performed flawlessly during cold startup. At ambient temperature, no errors or anomalies reported across hundreds of tests, with perfect waveform characteristics and all parameters meeting specifications. All laboratory tests were successfully completed, indicating ready-to-scale production for shipment. However, if the power is immediately restored and the system restarted under load after a power outage, it will instantly damage the input capacitor, destroy the main switching transistor, and ruin the rectifier bridge, resulting in a complete fire outbreak. Many engineers fall into this hidden pitfall. Debugging fails to identify issues, mass production leads to repeated repairs, and even after half a month of rework efforts, the root cause remains elusive, all ultimately attributable to a latent fatal flaw in the soft start mechanism. This is the most concealed yet most destructive fault among switching power supplies, LLC resonant power supplies, and high-power DC-DC converters. Thermal startup shock-induced board rupture caused by design flaws in the soft start circuit. The fault characteristics are highly specific and can be precisely identified. 1. Cold start, 100% normal operation. After prolonged power interruption and complete discharge of capacitors, the device starts smoothly on first power-up with no surge, abnormal noise, or error messages. 2. Hot start, 100% failure. Immediate failure occurs upon power-off restart or brief power cycling, typically involving damage to input filter capacitors and main power switching transistors. Severe cases may also destroy the rectifier bridge and PCB copper foil. 3. High load startup probability doubles. Slight loads may allow occasional startup, but under full or heavy loads, hot starts result in instant failure. Why can't laboratory tests detect it at all? This is the most problematic aspect for engineers. Both standard factory testing and prototype debugging rely entirely on single cold start tests, which precisely avoids fault-triggering conditions. The vast majority of R&D efforts are limited to power-on testing, aging testing, and steady-state load testing, with very few attempts at continuous rapid power-on, off cycles, or short-term thermal restart tests. This results in prototypes that are flawless in laboratory settings but frequently fail during mass production or on-site deployment at customers' facilities. A classic example of a design defect concealed in the lab yet manifesting explosively in real-world applications. All fault manifestations share a single root cause: improper design of the soft start circuit, resulting in residual voltage on the hot start soft start capacitor that remains undischarged. The core function of a normal soft start during initial power-up, it utilizes the charging and discharging characteristics of the soft start capacitor to gradually increase the PWM duty cycle, establish the bus voltage, and turn on the switching transistors sequentially, thereby limiting the surge current at startup and preventing power devices from being damaged by instantaneous high currents. The critical design flaw: during cold startup, the soft start capacitor and loop compensation capacitor are completely discharged with zero voltage. Upon power on, they charge gradually as the switching transistors activate sequentially, resulting in a smooth current rise and a stable system operation without any surge. Deadly hot start vulnerability: when the device is powered off, the main circuit loses power instantly, but the soft start capacitors, resonant capacitors, and compensation capacitors do not discharge immediately, retaining significant residual voltage. A common industry flaw: LLC resonant power supplies often omit or simplify soft start circuits, making them particularly prone to board damage. The control system operates without a buffer stage, delivering direct drive with a 100% duty cycle and causing the switching transistor to turn fully on instantly. Under these conditions, the input bus voltage remains at a high level, while the circuit impedance is extremely low, resulting in instantaneous peak current surges of several kiloamps. Electrolytic capacitors have extremely poor tolerance to transient high currents. They can instantly undergo breakdown, bulging, or even rupture. High voltage, high current conditions directly damage switching transistors, MOS and IGBT, leading to overcurrent damage in the subsequent rectifier bridge and ultimately resulting in complete board failure. A common industry flaw: LLC resonant power supplies often omit or simplify soft start circuits, making them particularly prone to board damage. During hot starts, many engineers mistakenly believe that LLC resonant structures inherently possess soft switching capabilities and require no additional soft start circuits, a fatal misconception. During a cold start of an LLC, the resonant cavity current builds up slowly from zero, appearing to indicate normal startup. However, during a hot start, residual energy remains in the resonant capacitor and inductor, combined with the residual voltage of the soft start capacitor, causing the resonant circuit to immediately enter a state of over-resonance and overcurrent oscillation upon restart. The instantaneous resonant current far exceeds the rated tolerance limits of power transistors and rectifier bridges, directly causing mass failure of primary power transistors and secondary rectifier bridges. It is also the primary cause of quality issues in mass-produced industrial power supplies, charging station power systems, and high-power adapters requiring repair. To address the issue of plate explosion during hot startups caused by soft start failures, this paper proposes a production-ready corrective solution covering 3 dimensions: circuit design, logic implementation, and testing procedures, aiming to eradicate the fault permanently. 1. Improve the soft start discharge circuit core improvement. All soft-start timing capacitors and loop compensation capacitors must be equipped with power-off discharge resistors. This ensures that capacitor voltage is completely discharged within 300 milliseconds after device shutdown, eliminating any residual voltage and guaranteeing that every power-up, whether cold or hot startup, initiates a fresh soft start process, thereby preventing full duty cycle surges at their source. 2. Add a hardware-based soft-start current-limiting circuit by installing an NTC thermistor and a relay bypass circuit at the high-voltage input terminal, which forcibly limits bus surge currents during initial power-up. Even if the control loop soft-start fails, this hardware layer still provides protection to prevent board damage caused by transient high currents. 3. Optimize the software startup logic by adding a power-on delay and a duty cycle ramp-up mechanism, preventing full duty output at startup. Additionally, implement residual voltage detection. Upon detecting bus residual voltage, extend the soft start duration to accommodate hot start conditions. 4. Dedicated optimization for LLC power supplies. The LLC-specific soft start circuit must not be omitted. A new resonant cavity energy dissipation circuit is added to rapidly release residual energy from the resonant inductor and capacitor upon shutdown, preventing thermal startup resonance over current. Simultaneously, the initial startup frequency is reduced to smoothly establish the resonant current. 5. Complete the full range of extreme test conditions crucial for defect avoidance. Mass production testing must include continuous rapid power on, off tests, and full load hot restart tests, as these are the only methods capable of revealing such hidden defects, thereby completely preventing prototype compliance from translating into mass production failures. Seemingly random board failure events are never due to component quality issues, but rather systemic vulnerabilities resulting from design flaws. Normal cold start performance does not guarantee circuit reliability. Only designs capable of withstanding extreme thermal restarts or heavy load restarts represent truly stable solutions for mass production. Follow ICWantOpen to unravel complex challenges in electronic manufacturing, from solution development and design to BOM management, debugging, and FA troubleshooting. For all electronic component and hardware issues, consult ICWantOpen first.